Hello, this is the Exam 3 review for Spring 2019. Okay, so these are the exam review questions. So with that, or the free answer portions. With that, so first up would be the is the molecule aromatic, anti-aromatic, or non-aromatic? Okay, so to be aromatic, you have to be in a ring, and every part of that ring needs to either be part of a double bond. It can be carbon-carbon, can be carbon-oxygen, either way. Has to have a charge or a part of a lone pair with that. So if it has that, with some infrequent exceptions, it's going to be eligible to be able to do the to move electrons around to it as part of, let's say, a resonance structure. The if it doesn't, say if it's a straight chain, or if it has a CH2 blocking it, blocking the chain, then, or the ring inside of there, then it's non-aromatic. But just having a ring and having conjugated double bonds around it doesn't mean that you're aromatic. You have to have the correct number of electrons in your p orbital, so you have to count up both the number of pi bonds in in the double bonds, as well as the eligible lone pair. Okay, and so if you're looking at so what you need is what's called the Huckel number, and so you can figure this out. You can memorize it, obviously, but I think I always like during this table. Okay, and so benzene we know is aromatic, and it's a classic 6. And so what we're going to do is we're going to go back and forth between the two. Okay, so 6, 8 is anti, 10 is aromatic, 12, 14, 16, and so on. Now this also works with 4 and 2. Okay. Other way you can do it is this is 1 pair, 3 pair, 5 pair, 7 pair. So if there's an odd number of pairs, then that's aromatic. If you have an even number, so this is 2 pairs, 4 pairs, 6 pairs, 8 pairs, then it's anti. That's the other way you can do it. Okay, so for this one here, right, all 4 of these carbons are part of a part of the ring. Okay, so we have 2 here and 2 here, so you had 4 overall, so that makes it anti. Well, this is benzene, so this is pretty easy, right? But you get 2, 2, and 2, right? So 6 overall, right? So this is obviously aromatic. Now for this one, we have 2 here and 2 here. Now if we counted the lone pairs, then that would be a that would make it 8, which is anti-aromatic. But the molecule really wants to be able to be aromatic. And so with heteroatoms, you can sometimes get a choice with these. So with carbon lone pairs, you got to count them. But for the but you don't always have to with heteroatoms. So nitrogens, oxygens, sulfurs, things like that. So for this one, what it does is that it really only uses these 2, and it basically hides the other 2 in order to be able to get to an aromatic state of 6. Okay. So it uses just one of the 2 pair. Okay, now for this one, right, so we have 2 and 2, but for this one, right, we've got this big CH2 group here, so it's blocking the ability for the electrons to go all the way around, stuff like that, and so this would end up being non-aromatic. Now for this one, right, so next up we're going to be doing some naming, and so you're going to need to know these base structures for the benzenes. Toluene is noted it only has 1 methyl group on it. So if you have multiple ones, those have other names, but the toluene just has 1. Now if you have multiple base structures, okay, there are priority rules. Now for what I'm giving you guys, these always have a higher priority than the toluene. Now there are set rules of, benzene sulfuric acid versus, it just says which you look at the table and sort of acetophenone versus benzoic acid, and there's tables. You don't need to know that. So if I have toluene and anisole, right, anisole is going to be the higher priority. So then that makes the methyl group that's on there just be a regular methyl. It's not a toluene. Okay. So first things first, right? So here's our molecule here, and there's actually a phenol right there. So the phenol. So that's going to be our that's going to be our base structure. Now the nice thing about base structures is I don't need to name the OH. It's understood that if you have a phenol, you have an OH there. Okay, so I don't need to name that. The OH is part of the phenol name. So the only side chain I have is this one, so you have a chloro. Now when you have a base structure, the carbon with the functional group hanging off it that makes the base structure, that's always going to be carbon 1. And then you're going to want to go clockwise and counterclockwise to get the lowest number set. So this one here, if you go clockwise, it's 1, 2, 3, 4, 5, 6, right? So it'd be 3. If you did it counterclockwise, it'd be 1, 2, 3, 4, 5, 6, and so it'd be 5, right? And so obviously you're going to want this one. So the overall name is going to be 3-chlorophenol. Okay. Next up with this one, right? There's no base structure, some of that, other than just the regular benzene. Okay, so that is going to be the base structure. So that means these guys here are just regular old side chains. So we have a chloro and we have a nitro. Okay, so now for this one, since we don't know which one's carbon 1, we got to figure it out. Okay, so we're going to give everybody a chance. Just like when we were doing cyclohexanes, we gave every carbon that had something hanging off of it a chance to be carbon 1. So here, if we get the chloro, right, so it'd be 1. We're going to go clockwise because that's going to get us to our nearest neighbor, our side chain neighbor, quicker. So 1, 2, 3, 4, 5, 6, right? So this becomes 1 and 3, right? So if we then said, okay, well, what if that's 1? Then we're going to want to go counterclockwise. So it's 2, 3, 4, 5, 6, like that. So it'd be 1 and 3, right? And so 4 and 4. So this is a tie, and there's no other way that we can resolve this tie. So if all else fails, there's no other way to resolve it. Then we look at the alphabetical, right? So we have chloro versus nitro. Chloro is first alphabetically, so we're going to pick these numbers because we're going to give the first alphabetically the number 1. So this ends up being 1 chloro, 3 nitro, benzene. Okay, there you go. Now for this one, right? So we're taking a UV sample, so we need to use this equation, Beer's law. I am going to give you that. It's going to look like this. I'm not going to tell you what the individual parts are, but I am going to give you at least this equation. Okay, and so right, so here we're looking at 340 nanometers. The extinction coefficient, right, is 6,300 per molar per centimeter. Right. Right, the wavelength 340 nanometers. Right, we're using a 1 centimeter cuvette, so 1 centimeter. In your reading is 0.025. So what we're looking for here is the concentration. So that's C. Okay, so we're going to put the absorbance here, right, 0.025. We're going to put the extinction coefficient, the molar absorptivity, so it'd be 6,300 per molar per centimeter. The path length, right, is 1 centimeter, which is nice because that cancels out. And then the concentration is what we're looking for. So we just divide both sides by 6,300 per molar. And when we figure this out, it'd be 4 times 10 to the minus 6 molar. Or if you want to be really fancy, you can say 4 micromolar. Okay, so here's the answer. Now we have this this value here for wavelength, 340 nanometers. We don't need it. It's not part of the equation, so don't put it in there. But that so there you go. Now for this one, so you're going to be getting 4 products. The way you do them is always the same. Okay, so you're going to want to attack with one of the double bonds, do the resonance structures, and then have the chloride attack the carbocation, and then you do the exact same thing with the other double bond. Okay, so I'm going to walk you through this. So this first one we're going to attack here, right? Push that there. Okay, now I'm going to draw in the hydrogens. You don't need to do this, but I'm going to because it makes it a lot easier to see. Okay, what's happening. So now you're going to want to put, right, okay, you're going to want to put this hydrogen here so that the carbocation is here, and you can get the resonance structure on here, okay? Because if we had the carbocation here, okay, and we put both of the hydrogens on this side, right? This CH2 was blocking access, blocking the molecule to be able to do a resonance structure where we can use this double bond to come over here. This is in the way. So we're going to want to put that hydrogen here so that the carbocation is right adjacent to the alkene here, so that we can go in and do resonance structure where we move that, slide that over. Okay, so we're going to make, it's a really bad H, sorry. Right, so we have a positive charge here, and then your other H there. Now, if the chloride sees this structure, right, it's going to attack there, right, to make this. Keep the colors the same. If it sees this structure, right, it's going to attack there. Right, so the chlorine's going to be here, right, and the H is going to be there. Okay, so here are two of your structures. Okay, now for the other side, so we're going to, so what do? Right, first step is we're going to have the double bond attack the H, kick off the chlorine. Next thing up, we're going to do the resonance structure, right, to get here, and then after we have the resonance structures, right, we're going to have our halide come in and attack to give our structures. So those are the three basic steps for this mechanism. Now we got to do this for the other side here, right? So that's going to attack there, kick that away. So what are we going to get? We're going to get again, we're going to want to put our hydrogen here so that the charge can be right there, right adjacent to that double bond, right? So Cl there. Now again, right, this carbon only has 4 bonds, right? So we can do a resonance structure where we move that over to make right, so there's a double bond there, right? So now the charge is right there because that carbon only has 3 bonds now, so the hydrogen's there. So again, if this chloride sees this structure, right, it's going to attack there, right, to make right. If it sees this structure, it's going to attack there. Right, the chlorine is going to attach there, and the hydrogen's there. So those are your 4 structures. How I did it, no matter what this structure looks like, you're going to go through the same process. So the way to study for this is to just go through this structure multiple times, this reaction, and get into the rhythm of these 3 steps. The double bond attacks, you get the resonance structure, then the chlorine attack, then the halide attacks to do the addition. Okay, so for this one here, draw the synthesized product, right? So So what you're going to have, right? So here is your diene right there. Okay, so it's going to look like this. That. Here is your here is your dienephile. Here is your 2. Okay. But since they're both, right? So since they're both of these are on wedges, that means they're on the same side, like that. And now you don't have to draw on the hydrogens, but well, so right, it says line, line, dash. So what's on or wedge? So that means the hydrogen's on the dash here and here, right? Because there's only 3 bonds shown, and you have 2. But for both of these, you have 2 regular bonds and a wedge. Right? So that means the hydrogen must be on a dash. So that means on the other side must be hydrogens. So there you go. So because these 2 are on wedges, they're both going to be on the same side. Now, if you put them both over here and the hydrogen's over here, that's fine. With that, so there you go. Now you are going to get some of these, right? So with that, so again, the reaction, right? This goes there, that goes there, and this slides there. Okay, so it's this bond, this, and this bond that we're making. But again, because these CH3 groups are both on the same side of this of the alkene, right? They're both going to be on wedges. Okay, don't forget this guy there. Now for this one here, so CH2, right? So this is the 3-dimensional way. If you want to draw it out like this CH2, we're going to say, okay, I'm going to put that on a wedge because it's got to get out of the way, right? So that's there, this is there, right? Right? So now if this is on a wedge, that means any group, if you have a group on here that has a pi bond, it's going to go in the opposite direction. So if this is going to go on a wedge, so if that's going to go on a wedge, this group here, right, it's got the pi bond, this has to be on a dash, which means this has to be on a dash. Okay, and that would mean that these guys here would have to be on a wedge, right? Because these 2 things have to go the same way. So if that's on a dash, this better go on a dash. So because this is going to go the opposite of where this bridgehead is going to go. If there's no bridgehead, it doesn't matter. It's only when you have the bridgehead. So that means this guy here had better be on a dash. Same thing down here. So that means this methyl group's on a dash. Okay, which means these hydrogens that would be on the other side. Now you don't have to draw them in, but I'm going to, just to show you, they would look like that. Okay. So this structure is the same as that structure there, just looking straight down it. Okay. Good luck.